class today. And I'm gonna see if I can upload your scores after class today. I'm gonna see if I can upload it. I think they're available for exam, what's that, exam 5 you took the last time? We need to post your scores.
How did you look? Is it okay?
I don't know, I haven't even looked at it. I'm assuming that you have your scores in your other courses yet? You're not, like in Poda and see, I haven't looked, they might not even be available yet. I remember one time it was all the way, it was Saturday or Sunday because I think there was a problem with one of them. So I'm hoping that they're available here. I'm gonna post them after class, okay? So today we're gonna start on a new topic, multiple dose kinetics, and that's in chapter 9 of your textbook. And don't let me go about 9:45 or so. I want to cover just enough material today to assign you some problems for next week's laboratory. And then hopefully on Tuesday of next week, we can finish up most of this topic, no later than Wednesday. But if I can give you a head start today. So I don't know if I've told everybody, but I know that there were some concessions made. We do this every other week exam, and the deal about not having a Friday's exam on the Monday, the Friday material on the Monday exam, I didn't agree to that, but I'm trying to work with it so we can let you see in my brain. So on Fridays, for the last several Fridays, we started on a new topic that's relevant to the next week's laboratory. So it is critical that that you're here on Fridays, like this past week in laboratory. Some of the confusion had to do with students missed Friday. They didn't come to class on Friday when I started talking about that particular topic. So here again today, I'm starting a new topic. I'm going to give you an assignment based on this topic for next week's laboratory. Does that make sense? So I'm going to try to work with, not including the Friday's material on upcoming exams, but we'll be starting new material on Friday. It's going to be relevant to the following week's laboratory. So that's what I'm trying to do. If I ever have to deviate from that and say, hey, it's going to be on the exam on Monday, hopefully, we only have a few more exams, so hopefully that won't happen, but please work with me. Okay, so over in chapter 9 of your textbook, they got erased here today. So in chapter 9 of your textbook is the section on multiple dose pharmacokinetics. And multiple dose regimen. Regimen, I'm just talking about, PK, pharmacokinetics. Okay. And what I want to do for the past couple of years, I've talked about multiple IV bolus dosing. We'll be giving an IV bolus dose, say every 4 hours, or every 6 hours, 8 hours. So that's where we're going to start. For the last couple of years, I haven't talked about multiple oral dosing, but I think we'll have time to talk about multiple oral dosing this semester as well. So we're going to talk about multiple IV bolus dosing to start in the model. Even after all of these years that I've been teaching, I still haven't come up with I don't see one in the textbook either, a good model for multiple IV bolus dosing. I'll just say multiple IV bolus dosing. And then if we have time, which I think we will, we'll come back and talk about multiple oral dosing, multiple IV doses. Okay. So we're going to base it on a simple one compartment model that we've come to know and love. So we're going to base it on this model, and since it's going to be multiple dosing, this is just something I made up. I'm going to draw the model on the board, for the next couple of lectures. I might not always write this in up here, but since we're going to be given multiple dosing or repetitive dosing, then I'm going to put a little time sign right here to show that we're going to be given So that X just means that I'm gonna be giving it more than one time. Remember, this is just the one compartment model with an IV bolus dose. Okay. So the little time sign that Felder made up just indicates that I'm gonna be giving it multiple times. A lot of the concepts, all of the concepts that we learned about the one compartment model with an IV bolus dose at the start of the semester apply to this model, this situation. It's just that we're gonna be giving the dose repetitively, like 500 milligrams of an antibody every 6 hours. So we give it at 9 o'clock in the morning. I'm just saying 9, it might start at 7. Then 6 hours later, we get the next dose at 6. That's what I'm talking about. We're taking the drug once a day, like digoxin, once every 24 hours. That's multiple doses, as opposed to just one single dose and it's over. Okay? All right. So, you know, what I'm going to try to do is explain a little bit of the concepts. This might be working better, I don't know. And then I'm going to come back and show you the equations, okay? So let's talk about some concepts, okay? So if it's IV dosing, when I'm going to see if I can write right up under here, but I don't want to go too low because I know it's problematic for some of the students that sit further away. Hopefully this whole damn thing ain't gonna do a backflip. So if we look at concentration versus time, what's a drug? What's a good antibiotic that we say we're gonna give it every 6 hours? I'm asking you, every 6 hours, normal dose. Dr. Capers is going to come in a couple of weeks and talk about vancomycin, gentamicin, or whatever the case may be. That we're going to give IV though.
Oh, okay.
Vancomycin would be one, okay,
Yeah.
but I don't want to give it. Okay. Well, let's just say we're going to give some drug every 6 hours, and we're going to give it by IV bolus dosing. Okay. I should have said multiple IV bolus. Because when Dr. Capers come in, he's going to talk about multiple dosing also, but he's going to be talking about multiple IV infusions, like short infusion. These are just IV bolus, instantaneous doses. So if I was going to give 500 milligrams every 6 hours, it'd be 500 milligrams just immediately, you know, an IV push every 6 hours. Right? So when I give the first dose, of this hypothetical drug, okay, it's gonna do like this, because it's first order, it's still first order elimination. According to this model, all of these, you already know what all of these mean. You know, amount of drug in the body, concentration, apparent volume distribution, first order elimination rate constant, metabolism rate constant, usually by way of the liver, but not necessarily. Some drugs are also metabolized by other organs, but the liver is the primary organ for metabolism, and then urinary excretion of the body via the kidney. So when I give that first dose, the concentration, and I'm just drawing solid lines, and we know that in pharmacokinetics we have data points, you know, specific concentrations. And of course, this value back here, I'm drawing the line kind of curved because presumably right now what I'm doing is assuming I'm on rectilinear paper. If this was logarithmic, log would see a similar log paper, that would be a straight line. Okay. But usually, like in your textbook, if they show this, like you should in the textbook, they're just going to show you the curve form because it's first order. Okay. And we know that drugs that are being eliminated first order, they go down in a curvilinear fashion. That was like our first or second lab. But we can make it look straight by applying the logarithm. We call you to put it on similar log paper. Okay, very good. So back up here is where C0 is going to be for the first dose, right? That y-intercept is going to be C0. And then let's just say I'm going to give a second dose. So this is the first dose. Let's say that C0 is also equal to what I'll call the maximum concentration after the first dose. I'm gonna call it C1 max. C1 max. And I'm writing kind of small to save space, so I don't want students in the back to not. So I'm saying that this C0, this initial plasma concentration, wouldn't that be the same as the maximum concentration after the first dose. I'm specifying first dose, because remember, I'm gonna come back with a second dose, a third dose, a fourth dose, so on. So this is the initial concentration, which you already know about from way back at the beginning of the semester. That's the initial concentration after the first dose. At 6 hours later, and I'm saying 6, but the dosing regimen is usually gonna be every 6 hours, every 8 hours, every 12 hours, every 24 hours. The things that you're already familiar with. We're usually not gonna be dosing every 3 hours. We're usually not gonna be dosing every 7 hours. Theoretically, you could, but the reason we dose in real life at 4 hours, 6 hours, 8 hours, 12 hours, and 24 hours, because that means that once we start the dosing regimen, we're gonna be giving the drug the same time every day. That make sense? So like, let's say we start at 9 o'clock in the morning, we're gonna dose every 6 hours. That means 9 o'clock in the morning, 3 o'clock in the afternoon, or 9 o'clock at night, and then 3 o'clock in the morning again, right? It's gonna recycle the same thing again. So then the next day it's gonna be 9 o'clock. You see what I'm saying? It's gonna stay on the same schedule. If there's no deviation by the patient or whatever. But that won't happen if you're dosing every 5 hours. The time is gonna be constantly changing every day. If you're dosing every 7 hours, it's gonna be hard to keep up with that. Does that make sense? So that's why convention, now if a patient is in the hospital or institutionalized, they might dose at some crazy, like every 5 hours or something maybe. Somebody's strictly keeping up with that but for, in normal situations, even in institutions, so it's gonna usually be every 4, every 6, every 8, every 12, or every 24 hours. Okay, that's the reason why. Using 2 hours will work too, but 2 hours, it gets to be a little bit inconvenient. You have to dose somebody every 2 hours, but that's another possibility. But you usually don't see a dosing regimen based on every 2 hours. But if it was every 2 hours, it'd be the same time around the clock and until the next days also, right? Okay. So here, in our case, we just assuming every 6 hours, okay? So at the end of that 6 hour period, I'm gonna give another dose, right?
Yes.
When I give another IV dose at the end of that 6 hour period, what's gonna happen to that concentration? It's gonna go up, down, stay the same. When I give another dose, it's gonna be the same size dose. It's gonna go up, exactly right. And it's gonna actually piggyback on the concentration that's already there. So we're gonna call this concentration right here, at the end of the dosing interval, we're gonna call that concentration C1 minimum, the minimum concentration after the first dose. We're gonna call it C1 min, C1 min. For those in the back that can't see, I just wrote C1 min, the minimum concentration after the first dose. I don't care how you write or whatever, y'all already know I'm not tripping on. I'm just telling you, that's C1 min. I got a subscript with 1 in min, but you don't have to subscript it. As long as you know what it means, I ain't gonna beat you up because you write it differently than me. So that's the minimum concentration after the first dose. Does that make sense? I gave that initial dose, it started here, and it goes down to some minimum. Why is that a minimum? Because right here at this point in time is where I'm going to give the second dose. And you've already told me when I give that second dose, the concentration is going to go up. So concentration after the first dose ain't gonna go no lower than C1 min. So when I get a second dose, the concentration is gonna shoot up to a new concentration. When I get that second dose. Check this out, okay. This time right here is what we're gonna call the dosing interval. In this case, we're gonna assume it's every 6 hours. But when I write the equations, that time right up under C1 min is the dosing interval. And traditionally in pharmacokinetics, it's abbreviated with the Greek letter tau, T-A-U. So in other words, the time from 0 to 6 hours, 0 hours to 6 hours, is the dosing interval here. And then at 6 hours, I give another dose. So you've already told me that when I give that dose, it's gonna shoot up to a new concentration. It's gonna go up there pretty immediately because I'm putting the drug in the body as an IV bolus dose. So it's gonna go up real fast to the new high. The equation I'm gonna show you in a few minutes is I'm gonna try to leave this drawing when I finish it. I'm trying to leave it on the board so you can relate the equations to it. But just think about it for a moment. When I give the second dose right here, wouldn't that new dose be, I mean, not the new dose, but this new concentration up here, which we're gonna call that new concentration that goes up to, we're gonna call that C2 max. In other words, the maximum concentration after the second dose. Because I gave the second dose right here. Does everybody see? I gave the first dose here. 6 hours later, I gave the second dose. So I'm gonna call this new maximum C2 max. Does that make sense? The maximum concentration after the second dose. Wouldn't it make sense that that maximum concentration after the second dose is gonna be the sum of whatever this concentration was at C1 min? Because I still have some drug left in the plasma. So C2 max is gonna piggyback off of what was already left in the body. So let's just say if I already had 5 milligrams per liter right here for C1 min, hypothetically. And then the new dose caused an additional 10 milligrams per liter from the new dose. Then this would spike up to 15 milligrams per liter. That's this concept is referred to as superposition. Okay, superposition. Yeah, in other words, and that doesn't just apply to this. It's just basically saying that the concentrations are going to be additive, superposition. So if this was 5, and then from the new second dose, I caused the concentration to go up an additional 10 milligrams per liter, then this C2 max would be 15 milligrams per liter now. Okay. So it's C2 max, and then right after I give the dose, it's gonna spike up, and then it's gonna start coming down also in the first order fashion. Okay. And then right here, at this place right here, that's gonna be what I'm gonna call C2 min, the minimum concentration after the second dose, because it's gonna, after it spikes up to C2 max, it's gonna start coming back down again. I'm gonna call that C2 min. And then I just do one more, and then we'll stop, okay? Look here, at that minimum concentration, okay, that's another dosing interval. That's why it's called a min, because the concentration can't go no lower than that, because what's gonna happen, I'm gonna get a third dose now, okay? After, this is 12 hours, so I'm about to get a third dose. I've already given 2 doses. I'm about to get a third dose. When I get a third dose, guess what's gonna happen? It's gonna spike up again to a higher concentration. That concentration up here is gonna be even higher than C2 max, because C2 min was higher, and remember we're stair-stepping, we're piggybacking on what was already left, okay? So we're gonna call this one up here C3 max, and then it's gonna decrease also, okay? And we'll call this one down here C3 min. Okay. Why is it a minimum? Because at the end of 6 hours, that would be 18 hours. I'm gonna give another dose, so that's tau again. Can you kind of see what's going on here? Conceptually, and understand what's going on.
Do you mind repeating what tau is again?
Tau is the dosing interval. So in this dosing regimen, if tau, by the way, tau is equal to TA, it's spelled TAU, that's the Greek letter. The Greek alphabet, okay? That's the dosing interval. So in the equations, we're gonna have this thing called tau. That's just the number of hours that I'm giving the dose. So in this case, we just assumed every 6 hours. So in this case, the way I'm drawing the board right here now, tau is equal to 6 hours. In other words, I'm giving the drug every 6 hours. If I was giving the drug every 8 hours, tau would be equal to 8 hours. It's the dosing interval. If I was giving the drug every 12 hours, tau would be equal to 12 hours, okay? So I just say, in this little illustration, we're gonna assume 6 hours, so you can see the 6 to 12 to 18. So at 18 hours, okay, I'm about to get a 4th dose now. At 18 hours, I'm gonna get a 4th dose, but I hope you can see what's happening for the first 3 doses, conceptually. So what's gonna happen is I continue to dose, I won't, but eventually, and my artwork is getting kind of sloppy here, but eventually, I could have exaggerated that a little bit more. I could have exaggerated that a little bit more for visual purposes. We're gonna reach it, we're gonna keep on dosing, and eventually we're gonna reach a so-called steady state. I'm trying to draw it up a little bit higher. That might be a little bit better. There wasn't anything wrong with what I drew the first time, but I want you to see that the concentration is gonna keep going up. And eventually I'm gonna reach a point where these maxes here, okay, here, and here, they're gonna keep going up to the same value. Notice down here early on, the maxes were getting higher and higher. Eventually I'll reach a point where I'm at steady state, and we're gonna have the equation to show what that is. But these values here, here, and here are what we're gonna call C steady state max. C steady state max. And then the minimums are gonna come down to the same values also at steady state. So these values associated with the minimums here, here, and here, okay? Those are C steady state minimum steady state concentrations. Okay? So if I don't change anything, I keep on giving the same amount of drug every 6 hours, okay? Eventually I'll reach a point, okay, where the maximum concentrations are the same after each dose, and the minimum concentration are the same after each dose. And that's kind of like what happened with the infusion situation. Basically at steady state, that means that the rate that the drug is being presented to the body is the same as the rate that the drug is going out of the body. See down here, before we reach steady state, okay, the drug was being, I don't want to say this. It was being placed into the body by those multiple doses. Drug was coming into the body faster than it was going out of the body. So that's why the concentrations kept building up. Because if I'm giving 500 milligrams of this drug every 6 hours, that's the rate that the drug is going in. Every 6 hours I'm giving 500 milligrams, but it's not coming out that fast. But eventually I reach a point where if I'm giving 500 milligrams every 6 hours, then I'm losing 500 milligrams every 6 hours also. And when that happens, I'm in steady state. Okay. So I've built up a certain amount of drug in the body, and that's not changing except that, you know, when I go from here to here, I lose some drug. But then we have what we call a maintenance dose. I don't know, you all discussed the concept of maintenance and loading doses. We talked about loading dose. But maintenance dose in therapeutics or pharmacology, you ever hear that term before? Maintenance dose?
So basically, it just prevents them from getting the pain again, so you have to.
No, that too, from a therapeutic point of view, but from a pharmacokinetic point of view, you know, every time I go from a maximum to a minimum, whether I'm at steady state or even before I reach steady state, I lose a certain amount of drug from the body, right? As I go from maximum to minimum, I'm losing drug because of these elimination processes, right? With a maintenance dose, the maintenance dose is just designed to replace that drug that has been lost. Okay, so for instance, let's say a patient on digoxin therapy. Okay, the physician might decide to give a loading dose. The loading dose, we already know the purpose of a loading dose, and we've discussed that in infusion. We're going to discuss loading dose with Ismail also. But the purpose of the loading dose is the same, is to quickly get us up into steady state, the therapeutic region, right? So we give that loading dose of digoxin, okay? And then when you see, which I think is still a common dose, digoxin 0.25 milligrams a day, still common, or 0.125? Digoxin, that's what.
We haven't covered that yet.
Huh?
Well,
Well, usually it's once a day for, you know, like congestive heart failure, or if a person has a rhythm, you know, because it's also used to treat rhythm problems like the heart rhythm. But it has a long half-life, and it's usually once a day. But a lot of times there will be a loading dose associated with digoxin therapy to quickly get the concentration up in the therapeutic region. And then the 0.25 milligrams a day is referred to as a maintenance dose. That's just to keep the concentration in that region, because if I don't replace what's been lost, the concentration is going to keep on going down. Okay. So the loading dose gets the concentration up real fast. The maintenance dose is designed to keep it up in the therapeutic range, near steady state. That's okay. So we have to give a maintenance dose. I just shouldn't say we have to, okay? But oftentimes the maintenance dose, is designed to keep it. Now we can start digoxin therapy without a loading dose. But just like we said with the infusion, now it's going to take approximately 5 half-lives to reach steady state, as opposed to getting up there immediately, which would happen with the loading dose. But in any case, you're going to still need the maintenance dose if this patient is going to be taking repetitive therapy. Loading dose or not, I want to have drug being lost from the body. You see that? Whether I give a loading dose or not, these processes are going to still be occurring. So if I want to keep the concentration at steady state, then I'm going to have to give a maintenance dose, okay, to replace whatever has been lost, okay? So I can keep on going from here back up to here. Okay? Every time I give a maintenance dose, it goes from a min back up to the maximum.
So how do you know, how much drug is, being lost in order for you to calculate maintenance?
I'm sure you, that's a good question. How do I know how to calculate the maintenance dose? Well, that's what we're gonna, when I show the equations that I'm gonna show you is basically gonna be revolving around the maintenance dose. Okay, so any questions about this conceptually? I haven't put any equations up here, and that's good. I want you to understand the concept first. All right. Yes. Uh-huh.
Yeah. So those steady state maxes all have the same
Yes. And all those C steady state mins have the same value. Right. But not as I'm building up to that. Yeah. Down here, C2 max, okay, is lower than C3 max. That's why I wanted to redraw it, when I said I could draw it better, because I wanted to emphasize that at steady state, the concentrations are usually going to be higher, but C steady state maxes, all of those values are the same. C steady state min, it comes back down to the same value. Another thing, I mentioned it, but it should be obvious here, is that when we write the equations, I'm going to try to leave this up here. Notice I always reach a minimum at the end of the dosing interval. And we talked about why that is, because at the end of the dosing interval, I'm giving another dose.
Yeah.
The same thing is true here. We reach our C steady state mins at the end of the dosing interval. Okay, the dosing interval goes from here to here. That's tau again. Okay, that's a tau value again. Okay, so we gave a dose here. It spiked up to a maximum, and then it comes back down to a minimum. So the minimum is always obtained at the end of the dosing interval. The reason for that, because at the end of the dosing interval, that's when we give another dose. And you've already told me that when I give another dose, the concentration is going to go up. So it can't be a minimum anymore. We conform with that? Okay, very good. All right, let's talk about a little bit of the math associated with this. When I give the first dose, when I give the very, very first dose, I grab my notes, but I don't really need it. I hope I'm going to teach you in such a way that this will be obvious to you also, okay? So the amount of drug in the body after the very, very first dose, we'll call it A1 max. I'm just going to put amounts initially, but I'm going to convert them to concentration. I'm going to put amounts because that's what I have in my notes here. So A1 max, the maximum amount of drug in the body after the first dose, is the same thing as what we come to know as A0, the dose in this model. Which, let's say A0, let's spell it out, is equal to the dose. Remember for a one compartment model, the amount of drug at time 0 in a one compartment model IV bolus dose is just the dose, okay? So the maximum amount of drug in the body is the same thing as the dose when we, after the first dose, okay? And then the minimum amount of drug in the body, I think I just do it once or twice for amounts, and then I want to put things in terms of concentrations, since I put this in context.
Yeah.
But to do that, ain't no big deal. All I'm gonna do is to divide the amount equation by the volume. Concentration is the amount divided by volume, okay? So the minimum amount of drug in the body after the first dose is just A1 max times e to the power negative KEL times what? Come on, look at me. Beautiful, tile, that's right. Very good. Autumn, and anybody that's recognize it. Tile does have time units. It does have time units, but the time that we're gonna put here now is tile. that time is gonna be tile, exactly right. Okay? So the minimum after the first dose is A1 max times e to the power negative KEL times a time, but that time is time. Right. That's when we reach that minimum. Okay? So can we write, and then I'm gonna do the rest of them. I'm gonna do the rest of them in terms of concentration. So can't we write then that C1 max, can we write that the maximum concentration after the first dose is this? Right, which we already know that. And then the minimum concentration after the first dose, just this over V. Right. Concentration is amount over volume, so that's still a true concept. Okay. And then when I give the second dose, okay, then C2 max for the second dose, when I get ready to go up here, C2 max is going to be equal to whatever C1 min is. That's why I left this up here, because you told me whatever C1 min is plus C0 again. In other words, I'm going to give the same dose, so it's just going to add another dose divided by volume to whatever C1 min was. Let's see if I can, let's just see if I can write it in terms of C1 max. C min plus C1 max, where C1 max is the same thing as C0. C1 max is the same thing as 0, so you can write it either way, okay? C1 min plus the minimum concentration after the first dose, plus, in other words, every time I give a dose, it's gonna add to the minimum by C0 or C1 max. Because I'm giving the same dose and it's being distributed throughout the same volume. So this is just the same thing as a C0 value. That's C1 max. So I'm gonna add that C1 max or C0 is gonna be added to every time I reach a minimum and I give the next dose, I'm gonna add C0 to it. I'm gonna add another C0 to what was ever left over. Does that make sense? Why are we doing that? Because the drug is just gonna distribute, that's gonna be the same dose and it's gonna distribute throughout the same volume. So that's why I'm adding C0 to the minimum every time, okay? So that C2 max, okay, is simply equal to the C1 min plus the C1 max. And then C2 min, okay, C2 min is equal to C2 max times e to the power negative KEL times what? Tau again, right? KEL times tau. Okay. So I hope you can see what's happening with this superposition usage is that, you know, we reached a minimum here. We gave another dose divided by volume of distribution. That took us up to this C2 max. Now C2 max is going to be decreasing over that 6 hour, over that tau time period, down to a min. So C2 min is just equal to C2 max times e to the power negative KEL times time. That's all that's going on here, okay? Now I'll write one more and then we'll stop, and I give you the general equations. The reason I'm teaching it like this is because I'm going to write some more easily used equations, but maybe harder to memorize equations. in real life, if you forget the equations, you can always come back to this approach, okay, to get to where you want to be. Okay. Remembering that idea of superposition. Okay. So when I get a third dose, I'm gonna get a third dose right here at this C2 min, and it's gonna jump up to C3 max. C3 max, and then I'll stop and, you know, C3 max is gonna be whatever C2 min was. It's gonna be what was left over from the previous C2 min, the second dose, minimum, okay? Plus C0 again, plus C0, or C1 max, whatever you wanna call it. C1 max and C0 are exactly the same thing. Okay, so here, when you studying, don't say, well, why do you put C1 max here? I put C0 so you know, okay? But C1 max and C0 are interchangeable. So every time I get the same dose, and it's distributed in the same volume, I get an additional C0 added to what was left over. And then C3 min, C3 min, it's just gonna be equal to C3 max times e to the power negative KEL times. Okay, I'm gonna stop right there, but that's all. You keep on going on, you know,
So this is
for the
not-
fourth dose, the fifth dose, sixth dose, but this is the idea of what's going on, okay? Maximum and minimums. Okay,
And once you keep doing it and you see you keep getting the same number, that's when you know you've reached steady state.
yes, when maximum and minimum, that's exactly right, okay? So this is just, if we want to reason our way through this type of graph. Let me give you the general equation, I said you don't have to keep on doing this type of situation, okay? So the concentration after some dose number n, where n is the dose number, n is the dose number. So it's gonna be a whole number. First dose, second dose, third dose, fourth dose, fifth dose, okay? So in this case, if I want to use the general equation that I'm gonna write, I'd be able to, if I wanted the minimum after the third dose, n would be equal to 3. If I wanted the minimum after the second dose, n would be equal to 2. N is the dose number, okay? So the general equation says that the plasma concentration is equal to A0 times 1 minus e to the power negative n KEL times tau over V times 1 minus e to the power negative KEL times tau. And then that's all times e to the power negative KEL times t. And this might be a good place to start wrapping it up. Yin, did you get here? Yin here?
Yes.
All right, give me 5 more minutes and Professor Yin and I are gonna get these out. Okay, now let me relate this equation to what we've done over here. So this is what you need to memorize for the course or whatever the case may be. What I'm saying is, in real life, if you ever forget this equation, you can go back to this approach to get to where you want to be. It's just gonna take longer with this approach. So, if I wanted to know the constant, well, let me do it this way first. Maximum and minimum. Let's deal with maximum and minimum, since that's what this is, okay? In this equation, T is the time after I give the dose. So don't get T mixed up with tau. This is tau, this is tau. Tau, this is a T. T is the time after I give the dose.
What do you mean by
I'm gonna tell you exactly what I mean, but all these are all showing up maximum and minimum. But what if I wanted a concentration right here? Is that a maximum or a minimum? Everybody see what I'm saying? What if I wanted to know the concentration at 3 hours after the third dose? Huh? What if I wanted to know the concentration at 2 hours after the second dose? That would be this T right here, is the time after the dose. Amen?
So
Oh, that's okay. So T is the time after the nth dose. So at 2 hours after the second dose, N would be equal to 2, but T would be equal to 2 hours. At 3 hours after the second dose, N would still be equal to 2, but this T would be equal to 3 hours. At 4 hours after the second dose, N would still be equal to 2, but this T would be equal to 4. Does that make sense?
What is N again?
Say that, what's that?
What is N again?
The time after the dose.
N.
N is the dose
Dose
number.
number.
Oh, you say N, I'm sorry, Renee, yeah. N is the dose number, yes. Thank you all, class, for correcting me, okay? I really appreciate it. That's what I want you to do more of, because I do screw up sometimes, a lot of times. Okay, so N is the dose number, T is the time after I give that dose. We okay with that now?
Yes, it
Okay, let me ask you this. In this dosing scheme, T would, every time I reach a max, you can look at dose number 1, if you want to, over here on our scheme. At every maximum concentration, what's the value of T? At T equal what numerical value am I gonna be a maximum?
is. In order, and it goes with 6.
Okay, let's just focus on dose number 1 and you can answer my question. T is a max, concentration at a maximum at T is equal to what value in dose number 1? No. Who says 0? Because the one saying 0 is seeing something that I want you to see. Every time I give a dose, the concentration is gonna be at its maximum value times 0. It's an IV bolus dose. So that concept that we learned early on, you know, where we reach a max for an IV bolus dose at times 0, that's true after every dose. Every time I give a dose, the T in this equation is equal to, the T is equal to 0. The time ain't changing. If I'm dosing every 6 hours, the time is gonna be the same. But at every maximum, T is equal to 0. At every maximum.
But in the graph, it doesn't show 0 actually.
You should, that's why I told you to bring attention to the first dose. You know, to see 0, I call that C1 max. The same thing that for that maximum concentration at time 0 is the same thing for the C2 max, the C3 max, so on and so forth. So every time
Because we're restarting.
yes, we start the clock after we give every dose and T is resetting. I said the time after, yeah. It's resetting after each dose. I said T is the time after the dose. So every time I give a dose, T resets. T resets, you know.
So T cannot exceed tau.
T not going to ever exceed tau. Not in this discussion we're talking about right here. No, it's not. No, because T is resetting after each dose. You know, I can go, you know, 1 hour, 2 hours, 3 hours, 4 hours, 5 hours, 6 hours after the second dose. But if I'm dosing every 6 hours, I don't need to talk, unless I'm ending the dosing regimen, I don't need to talk about 7 hours after the second dose because at 6 hours, I'm gonna give another dose. I'm gonna give the third dose. T is gonna reset. And the N is gonna go up by 1. Every time I give a dose, the N goes up by 1 in this equation.
This is the dose number.
Yeah, it's a new dose, an additional dose, okay? So every time I'm at a maximum, okay? Every time I reach a maximum, I'm gonna say C max N is gonna be this equation, e to the negative n KEL times tau over v times 1 minus e to the power negative KEL times tau. And you just told me, I had to pull it out of you, but that's okay, that at a maximum, T is gonna be equal to 0, so if T is equal to 0, then this e to the power negative KEL times is equal to 1, right? So every time I reach a maximum, here's the equation that applies. At a maximum concentration. So if I want to know the maximum concentration after the third dose, now, check it out, this top equation covers everything. If you understand this top equation, you don't even need to memorize the rest of these, but I'm showing you, even for the maximum concentration after the dose number N, you don't need to memorize that. If you recognize that T is equal to 0 at every maximum, then this equation just becomes this equation. For minimum concentration after some dose number N, So the maximum concentration after the second dose, you put N equal 2 into this equation. You put the dose in there or whatever that is, and do the math. By the way, A0 over V is the same thing as C0 in this model. So this equation could also be written as C0 times 1 minus e to the power negative KEL, negative N KEL times tau, and leave the V out. If I substitute A0 over V is equal to C0. That's why we keep on adding that C0 to each one. You follow what I'm saying? To these. Because we got C0 in this equation. I want you to see C0 is in this equation. A0 over V is C0. Dose over V is C0.
Will time change when it comes to minimum? Or still?
The time is defined exactly as we said. Every time I give a dose, time after the dose resets. We reach a minimum at time, we give a new dose, the time resets to 0. But N goes up by 1, because we give a new dose. The minimum concentrations, see minimum after the M dose, it's just the maximum concentration, C max N, just like we talked about over here. C max N times e to the power negative KEL times time. So the minimum is just this equation right here, times e to the power negative KEL times time. Now you've already told me, I'm just showing you the equation. We've already talked about the concept. So every time I reach a minimum, it's wherever I was at a maximum, times e to the power negative KEL times time. That's minimum. Eventually, as the number of doses increases, okay, as the number of doses increase, what's going to happen to this term right here? As N increases, get bigger, smaller, stay the same. Come on, I heard some people say same, no. You say that on the next exam or a final exam, you're going to lose 2 points unnecessarily. This is a negative exponent, so as N increases, KEL and tau is not changing in those numbers. It's getting smaller. So as I give successively higher doses, N goes from 1 to 2 to 3. It's getting smaller. So eventually, that circle term right there is going to become so small, I have essentially 1 minus 0. It's never going to actually go to 0, but it's going to be a small number. Okay. And at that point, I'm at steady state. So therefore, C steady state max. C steady state max, this term right here is going to be negative. So it's not going to be my C steady state max equation because I've given enough doses now. Okay. So C steady state max is just equal to A0 over V times 1 minus E to the power negative KEL times tau. You say, well, what happened to this part? Well, if it's a maximum now, remember this T is equal to 0. That's why I'm saying, if you know this top equation, all these other ones come from the top equation. This is the key equation. This is the parent. The rest of these are children, like the old folks say. Not children, but children. All these other ones come from, and C steady state min, let me write it the same way. C steady state min, it's just equal to C steady state max, which is this equation. It's just equal to C steady state max, which is the same thing as this right hand side of the equation, times e to the power negative KEL times what? Anybody? Beautiful. Tau. That's not reaching. I still reach the minimum, even if I'm in steady state at tau. That's it. Make sure you write tau there and not T.
Yeah.
So these are key equations. Let me give you a few problems to start working on, and we're out there. So this material is over in chapter 9. At the end of chapter 9, there's some learning questions. I'm going to assign the whole shebang. I don't think there's any graphing to do. So hopefully in laboratory next week, we'll get further into the assignment. But don't come naked, okay? Work on this before, what's that? Next Tuesday and Wednesday. So at the end of the chapter, there's some questions. So on page 225 in my textbook, so look at, take that back, fella. Don't just look at it, because you all say, well, you said look at it. Do. Start working on number 1, number 2, number 3, 4, 5, 6, 7, 8, and 9. I'll repeat those. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1 through 9, that's you. But the rest of them, you know, that's icing on the cake, you know. But these are the ones I'm holding you responsible for, whether we do them all in lab or not, okay? So if we don't cover them all in lab, you can still come back after lab or whatever. I'm talking, and ask me any questions you have about it, okay? But hopefully we'll get a chance to cover most of these in lab, because we ain't got no graphing to do. And as you know, the graphing and my antics, you know, checking the graphs and answering questions about the graphs, you know, it takes a little bit more time. So these are just strictly mathematical problems, okay? Let me see if I can cue you in a little bit. Now, you can read some stuff in the book, but after today's lecture, you should be able to answer number one. Number one asks you to calculate C max and C min and C average. By the way, I didn't talk about average yet. I'll talk about it Monday, okay? You should be able to calculate C max and C min. That's A and B for one. Now, that should be C steady state max and C steady state min. They didn't put that in the book. In the book, it just says C max and C min, so that's an omission. Yeah, and for A, they really want you to calculate C steady state max in your assignment. And for B, they want you to calculate C steady state min, okay? This is chapter 9. Number 2, you should be able to answer based on today's lecture. Number 3, you can read in the book, but they talk about average steady state concentration. I didn't give you the equation for average, but I'm gonna give it to you now so you can get the average steady state concentration. In the book, they call it a C steady state average or something like that. But I just use it, you should be seen as a C with a hat on top of it, says C bar. That's just equal to the dose, A0, divided by V times KEL times tau. That's the average steady state concentration. Dose divided by V times KEL times tau. So, I'll talk more about that. Remind me, Tia. Remind me on Tuesday to talk more about it. But as you working your problems, you can still go ahead on the calculator now, even if you don't understand it. So you have to be able to answer number 1, number 2. Number 3 we haven't talked about yet. Number 3 and number 4 you might not be able to answer unless you read it in the textbook, but we will come back and talk about those things. Number 5, I've already told you the purpose of giving a loading dose. Number 6, you can read it in the book, but I'll talk about it on Tuesday. We haven't actually talked about calculating a loading dose yet, but I told you we're gonna talk about that. Number 7, you should be able to answer just from therapeutics and pharmacology. And number 8, we just talked about. They ask you to calculate the concentration 1 hour after the 3rd dose. Use the equation we just talked about, okay? And number 9, you should be able to work with that also. That's C infinity max and C infinity min. C infinity max is the same thing as C steady state max. In the book, they're calling it C infinity max. They're calling that because you've gone from the n number of doses, it's kind of like infinity. And then they got something they call a C min infinity. That's the same thing we were talking about, a C steady state min. Okay. So if you run into those symbols in the textbook, I don't want you to say, oh, Dr. Phil didn't talk about those. Okay, C infinity max, just like right here, C infinity average is the same thing as the average steady state. In the textbook, they use the C infinity stuff to indicate steady state. In the textbook, they use the infinity symbol to indicate steady state. Yes. Let me start with that. Okay, this is the Word file with the answers to the questions and the problems for exam 4. Okay. That's good. No problem.